We're going to continue on our journey, and we're going to leave inverses and we're going to start to look at some different concepts. We're going to be working with exponentials, and you're going to need a calculator for this. I suggest using the Web 2.0 calculator that you've seen me use a few times in the different videos I've posted. You can do a quick Google Web 2.0, so 2.0, and it will pull up that calculator. We're going to define and graph exponential functions. You can use desmos.com for graphing, and we're going to solve them as well as looking at applications involving growth or decay. So if I want to use a calculator to find the value of an exponential, I can look at these three values, and in Web 2.0 you would hit 2, shift, and the number 6, which should get you the little hat there, to the 4.5 power. This isn't a power I can really compute by hand. I'm not sure what 2 to a 4.5 power is, but when I go into the calculator, I can do this. Now, a caution, for B, I would enter it as 2, shift 6 to get the hat to appear, open parentheses, negative 1.1, close parentheses. The use of parentheses around negative numbers just helps the calculator know exactly where they are, and it builds a good habit for us to continue to build on as we move through this chapter. An exponential function is going to be a function with a base that's a numeral and an exponent that's a variable. I have to have positive numbers for this to work. If I want to graph 10 to the x, I can go to desmos.com and graph 10 to the x. Or I could also create a table of values to see how this looks. Now, if you go on desmos.com, you're going to type in 10 to the x exponent. You should also see this. You should notice that every single exponential is going to cross the y-axis at this point, at 0, 1. Because 10 to the 0 power is 1. Any number to the 0 power is 1. So the y-intercept of all of these exponentials is always going to be that specific value. Same thing here, 1/4 to the x. I'm going to go in desmos.com. I'm going to enter it. It's going to cross the y-axis again at that 0, 1 point. What's different in this question is that the value of a is between 0 and 1. Because the value of a is between 0 and 1, I get this inverted image where it's backwards. So this would be a different type of exponential equation. When a is between 0 and 1, it's going to go down. Remember, this is an asymptote here on the x-axis, so it's going to get really close to it, but it's never going to actually cross that x-axis. So a few characteristics that we talked about. 0, 1 is always going to be the y-intercept. They are going to be 1 to 1. If the value of a is greater than 1, it's going to rise. If it's between 0 and 1, it's going to fall. The graph in each case is going to approach that x-axis but never cross it or touch it. The domain is always going to be negative infinity to infinity, and the range from 0 to infinity, unless I start shifting things. So what does 2 to the 4x minus 3 do? Well, I can do that process, or I could type it in desmos.com, and I'm going to see that now that y-intercept has shifted. Because if I plug in a 0, I'm going to get 2 to the negative 3. So that's why things are going to be a little bit different here. It's because I've changed the exponent from just being an x to a 4x minus 3. But it still follows the same characteristics. It's going to rise because it's 2, which is greater than 1. Now, to solve exponential equations in this form, a to the x equals a to the k. Notice the base has to be the same in each one of these. So if I wanted to solve 9 to the x equals 27, I need to figure out, is 27 a power of 9 or a power of something that both of those can be written as? So I need each side to have the same base. Then I'm going to simplify the exponents, set them equal, and solve. So looking back at what I just did over here with 9x to the 27, 27 is not a power of 9. Okay, it's a multiple, but not a power. But 9 can be found by 3 squared. 27 can be found by 3 cubed. So I could write these as the same base with the number of 3. So here, 25 cannot equal 125, right? There's no power of 25 is going to give me 125. But 25 is 5 squared. So what is 125? Well, let me pull out my calculator. 5 cubed, if I type that in the calculator, it's going to be 125. So I can write these as powers of 5 I can use my exponent properties to do 2 times x, which is 2x. Now that I have the same base, I can set the exponents equal, and I can solve for x. So the trick here is going to really be knowing your powers, and you may have to do some experimentation with the calculator to help you solve these. So if I want to check that the solution is 3.5, I could plug that in and make sure that I get the right answer. So this is a good skill in the lab because you're not wanting to get a bunch of solutions wrong so that you get new questions, or you don't want to miss questions on your test. So you can definitely plug in to check your work. Here I have a similar situation, so I have to write them as powers of 5. But now when I follow the rule, I have to distribute that x minus 2 to the 2. So both of those have to get that 2. So this would be 5 to the 2x minus 4 equals 5 to the 3x. Because my bases are alike, I can set the exponents equal, and then I can solve for x. So I would distribute the 2, 2x minus 4 equals 3x. I would subtract 2x from both sides to get x equals negative 4. To check my answer, I'm going to go ahead and plug that in just to make sure that I got the right answer. It's true on the right and the left, so it is the correct answer. What about this one? This is kind of tricky, right? So 32 is not a power of 4. 1 over 32 is really confusing, right? But 4 can be written as 2 squared. So I have to figure out, can 32 be a power of 2? So take out the calculator and start working with it. And we find that 2 to the 5th is 32. Remember from our exponent properties that a negative exponent creates that flip. So when I have 2 to the negative 5, that's the same as 1 over 2 to the 5th. So that's where this came from. And then I'm going to follow the rules and set the exponents equal and solve. I can check my work, and I find that it's true. So be careful when you start seeing a regular number go to a fraction. That right off the bat should give you a clue that you're going to have a negative exponent there to work with. All right, so for this one, what can I do here? Well, the problem that I'm looking at is 3 is related to 9, and 4 is related to 16. So if I do a negative exponent, that should work in my favor, right? Because if I did the negative 2, that brings the 3 to the top and puts the 4 in the bottom. 3 squared is 9, 4 squared is 16, so I didn't really change the problem. So I have x equals negative 2, I check my work, and it is true. So really be on the lookout as you go through this week for these negative exponent instances. Now, to use exponential functions that involve growth and decay, if I'm talking about exponential growth, I'm talking about numbers that are greater than 1. So if I'm talking about decay, I'm talking about the case where the a value is between 0 and 1. So if I want to be able to approximate this, I'm looking at the years, and I want to know how well does a function approximate the actual figure of 394. Well, I'm going to plug in the 2012 value for my x, because that's what they tell me x stands for, and I get about 390. That's a pretty good approximation considering the actual value is 394. So it's slightly below, but it's pretty accurate. Here, I have another situation where I'm dealing with exponents. I have that exponent of negative x, which would be 1 divided by 1 over that, which means this would actually be a decay function, because I would have 1 over that value inside the parentheses. If I want to know how it approximates 8,000, I'm going to go ahead and plug in 8,000 for x. I'm going to use Web 2.0. This is not by hand work, guys. Not by hand work. And you get 355. So the pressure is going to be approximately. Why do I say approximately? Because I'm kind of guesstimating here. I'm not getting an exact value, but I'm working with what I have.